Good evening, everyone. Welcome at our second lecture on astrochemistry, from dust till down, how solids affect cosmic life. This evening we have three speakers for you. We have Dr. David Gobrecht, we have Dr. Marie van de Sande, and Robin Baeyens. These lectures are organized by the KVCV, or the Royal Flemish Chemical Society, of which I'm going to give you now a short introduction. The KVCV is a chemical society within Flanders, so the northern, the Dutch-speaking part of Belgium. And we are a community of chemists in Flanders and far beyond, because everyone can become a member of our society. Our members are mainly students, PhD students, academics, teachers, and professionals. So we do represent and strive to support everyone in chemical education, industry, and society. We mainly organize lectures about popular scientific topics for the general audience or more domain-specific workshops. After our lectures, we mainly have a networking reception, which is, of course, not possible, unfortunately, in these online editions. Here you have an overview of our upcoming events. We strive to organize each month a lecture. Next month, we will have a lecture on explosives, chemistry, and technology. And next year, we also planned a company visit to Cargill in April, of course, if the COVID situation allows this. For more information or registration, you can always visit our website, kvcv.be/calendar. Mens en Moleculen is our magazine, which is distributed to all our members once a month. So this means that we have 12 editions a year. And in this magazine, you can find news about the chemical industry, about academics, about our own activities, some scientific advancements, and much more. If you are a member of the KVCV, then you're automatically also a member of EUCHEMS, the European Chemical Society. And as a member of EUCHEMS, you have discounts on various activities endorsed by EUCHEMS. If you're a member of the KVCV, you have reduced prices at our activities. You also receive our magazine, Mens en Moleculen, as already mentioned, each month. But you're also part of the chemistry community, which helps you to extend your knowledge and broaden your network. If you're interested in a membership, I recommend you to visit our website, kvcv.be/membership. And for PhD students, you can already become a member for only €12 a year. For more information, you can always visit our website, kvcv.be. You can also reach us via our social media channels. We have a Facebook page and a LinkedIn page. We also have a YouTube channel on which our lectures can be rewatched afterwards. This series of webinars is supported by Chemistry Europe. So here you can see their journals, which might be of interest for your next publications. We are now about to start our webinar. If you have any question during the webinar, you can always ask them in the Q&A section at the Zoom platform. And after the lecture, we will ask them to our speakers. So let me now introduce you to our speakers. The first speaker is David Gobrecht. David obtained a master in theoretical physics at the University of Basel in Switzerland, and then continued his education at the PhD level at the same university on the subject dust synthesis in evolved oxygen-rich asymptotic giant branch stars, or AGB stars. Afterwards, David moved to Italy for a postdoctoral research fellowship at the observatory INAF OACTE in Teramo, where he advanced the state-of-the-art in AGB modeling. Now, David is a postdoctoral ERC fellow at the Institute of Astronomy at the KU Leuven under the grant Aerosol, Astrochemistry of Old Stars, Direct Probing of Unique Chemical Laboratories. Our second speaker, Marie van de Sande. Marie obtained a Master of Science in Astronomy and Astrophysics at the KU Leuven in 2014. She then continued her PhD level education at the Institute of Astronomy at the KU Leuven under the supervision of Professor Leen Dessin. Currently, Marie is a postdoctoral FWO fellow, and in 2021, she will start a new adventure in Leeds, where she will become a Marie Curie Fellow. Marie's research focuses on the development of theoretical chemical kinetic models to investigate the chemistry in dusty winds around AGB stars. And our third speaker, Robin Baeyens. Robin also obtained a Master of Science in Astronomy and Astrophysics at the KU Leuven and was awarded the 2018 Odyssey Prize by the Belgian Senate and Federal Ministry of Science Policy for his master thesis on vertical mixing in the atmospheres of hot Jupiters. Currently, Robin is FWO PhD Fellow at the Institute of Astronomy at the KU Leuven. His research focuses on modeling the climate and determining the chemical composition of the atmospheres of exoplanets. This research is conducted in collaboration with the Max Planck Institute of Astronomy in Heidelberg. And now I will give the words to our first speaker, David Gobrecht. So David, the screen is yours.
Hello, everybody. Give me a minute to share my screen. Does this work now? Yes. Hello. Good evening, everybody. I want to thank Nathan very much for this very kind introduction in the name of all three of us. And also we thank the KVCV to give us the opportunity to talk in this evening and have so many nice participants in this talk. So the chapter 1 of this presentation will be the dust nucleation, or how we come from the gas to the solid phase. So what does astrochemistry mean? So astrochemistry is composed of two words. One word is astro, which comes from the Greek word astron, which means star. And we have related fields, which is the astronomy, which is rather observationally motivated, and astrophysics and cosmology, which have rather a theoretical background, but there's many more related fields. I didn't list them all. And then we have the term chemistry, and that derives from the word alchemy, which potentially has an Arabic origin, but this is not fully clear. And this is derives from alchemy. As I said, this is an Arabic word, and it deals with the composition, properties, and change or transformation of chemical substances. And its related fields here are molecular dynamics, quantum chemistry, and chemical kinetics. And I want to mention also one rather sarcastic statement that I once heard about chemistry, and that was, yeah, chemistry is simply the physics of the valence electrons, but I think this is not true, and chemistry is much more than that. So astrochemistry is not only combining astronomy and chemistry, but it's on the other hand also interdisciplinary, because the tools are. So on one hand, we have, we have the theory, which mainly deals with calculations and numerical simulations of molecular systems. And me, myself, I consider myself as a theorist, But of equal importance are observations that are performed usually with telescopes. And our boss, Lynn Desin, she is leading now the Atomium program, which is one of the largest observational programs for evolved stars that is conducted at the ALMA telescopes in Chile. And of equal importance are the laboratory experiments that are mainly investigating meteorites. So they're hunting for meteorites in the desert. If they don't find one, they can also produce an analog. And also in the lab, what is important for us, they measure reaction rate for astrophysical relevant reactions. And here you can actually see an atomic force microscope picture of a stardust grain inside a meteorite. So now we know astrochemistry is very interdisciplinary. I will start with telling you a bit more about the astronomical part of the astrochemistry. So stars are not static, but they evolve. Here in this nice courtesy, we have actually depicted the evolution of a star. Here in the middle, where you see this kind of cloud-like structure, there a star is born. And depending on the initial mass, they have different evolutionary tracks. So here on the right-hand side is the stellar evolution track of initial solar masses. And on the left-hand side is depicted a star which has less than 8 solar masses initially, like our sun. This yellow dot here should represent the sun. And what we're mostly interested in our talks here now are evolved stars of low and intermediate mass stars. So why do we put together the low and intermediate mass stars? Because actually their evolution is quite similar apart from the way they burn the heliums in their core. But this is too much detail, and you will see this slide or this picture, you will see it a few times again this evening, I'm sure. So what I wanted to mention, both evolved stars in the high mass regime and in the low mass regime, they have different nuclear burning stages and mixing processes, which also lead to the fact that their surface composition change over time. So, evolved stars, what are they? So in the end, what we see here in this nice illustration made by Katrien Kohlenberg, which is a Flemish researcher, is a star here depicted as a fire devil. So a star is actually nothing else than a gas or plasma sphere which makes nuclear fusions inside in order to make its energy that can be radiated away. However, these evolved stars, they also pulsate. So what does pulsation mean? Pulsation is actually a more or less regular, and with regular I mean periodic, oscillation of the stellar surface. This actually has the effect that the luminosity or the radiation field of the stars periodically changes. And that also leads to a rather complex chemistry, which I will address in a few slides later. And in addition to this complex chemistry, we have also a mass loss or an outflow, or if you wish like to say it, a pressure-driven wind. And that's actually astonishing because usually a star has a gravitational field and keeps everything together. So there must be something that overcomes this gravitational pull of the star. And in these winds also dust is detected, so solids. So these matter and mass losing stars are ideal astrochemical laboratories. And if I now come to the low mass evolved stars, they are called AGB stars or asymptotic giant branch stars. So as I said, these are late type stars with a moderate or low stellar mass. They are rather old, that's why they're evolved. So that's about 10 billion years. They're really large as compared to the sun, so about 400 to 500 solar radii. And they're rather cool, which makes them red. Hot stars are rather bluish and cold stars are rather red. This is actually contrary what you think about when you, for example, look at your sewer and your pipes from the water, where red is hot and blue is cold. So these AGB stars have a mass from 1 to 8 solar masses, and they have these mentioned radial pulsations or oscillations. And they drive a dusty mass loss. And this mass loss has a rate of about 10 to the minus 7 to 10 to the minus 5 solar masses per year. Now you might say, well, this is not so much. This is 1 part per million per year. This is a rather low rate. However, this rate exceeds the mass converted in radiation energy in the inside by nuclear fusion. And now you say, how can mass be equal to energy? Well, it can, according to Einstein's famous formula, E is equals to mc squared. So now I mentioned already these radial pulsations, and they are depicted in these plots. So here on the x-axis, we have the time component, and on the y-axis, we have the radius component. And here on the left side, we have a model of the atmosphere of this star, of an AGB star, which has no dust component. So this is a purely molecular atmosphere. And if we look at trajectories within time of this atmosphere, then we see here actually oscillations that are purely periodical and actually always return to their initial point. So in the end, with this model, we don't drive a mass loss, or we don't have an outflow in net. However, if we introduce solids or dust grains, which is here indicated in this blue to red color means a high degree of condensation, then we are able to drive a mass loss or an outflow with this pulsation. You can see here gradually these red streaming lines, they go outwards. So we have a net mass loss. So what you should conclude from this slide is actually that the formation of dust grains is crucial for driving an AGB star wind. And the reason for this is that the dust grains present here, they provide a sufficiently large cross-section, or in astronomy, we say opacity, for these stellar photons to transfer momentum and then to actually overcome the gravitational pull of the star. So turning now to the chemistry side. So the chemistry in the atmospheres of these AGB stars is primarily controlled by the atmospheric C/O ratio. What means C? C is carbon and O is oxygen. And this is a consequence of the high bond energy of the carbon monoxide molecule, which is actually the highest bond energy for a diatomic molecule, and it's above 1,000 kilojoules per mole. And if we look here at the electronic structure of CO, then we see this carbon monoxide is triple bonded. And I wanted to mention here also one of these bonds is a dative bond given by the oxygen atom. So in the end, this makes this carbon monoxide molecule having a lower dipole moment than initially expected. And as a consequence of this high bond energy, and the CO ratio controlling the chemistry, we have a dichotomy in carbon over oxygen is smaller than 1, which we also call oxygen rich. Here we have oxygen-bearing molecules like water or OH or sulfur oxides, but also silicon monoxide. And the dust that I previously addressed is also oxygen-rich with silicates, but also TiO2, so titania, and alumina, which I will address a bit later. On the other hand, we have carbon-rich environments where the C over O ratio is bigger than 1. And here we have acetylene, HCN, CS, and in mainly carbon-bearing species for the molecules as well as for the dust. But as you might remember from some of the previous slides, first of all, the surface composition might change over time. So an oxygen-rich atmosphere can become carbon-rich, and vice versa, a carbon-rich atmosphere can become oxygen-rich. Also, HCN and CS has found in smaller amounts in oxygen environments, and water has been found in carbon-rich environments. And that actually cannot really be explained by equilibrium chemistry, but there the pulsations and non-equilibrium chemistry and photochemistry might play a role. That's why I indicated here this blizzard. So now you have seen here in this slide atoms like carbon and oxygen, molecules and dust. And to give you a better impression about the structure of matter or the size of the matter, I have created this slide where you actually see here on the left side atoms. Here I depicted aluminum, hydrogen, and oxygen. And these atoms, I should better say they are isotopes, because the isotopic anomalies are important for astrophysicists because the isotopic ratios are different than on Earth. And classical, if you want to describe the atoms, you take the so-called solar abundances, which are composed of mainly of hydrogen and helium, which make up almost 99% of the atomic mixture, and the rest, 1 to 2%, is left over for other elements like carbon and oxygen, but also aluminum. And a bit more sophisticated models predict also different abundances, and they depend then on the stellar mass and also on the evolutionary state. So you will have a changing C over O ratio, whereas if you take the solar abundances, you just have a fixed one. So if we increase the size and combine these atoms, we end up with gas phase molecules, where I depicted here ALOH, H2O, and CO. And the gas phase molecules, they're connected to dust grains essentially by molecular clusters. So let me please define what a molecular cluster is. A molecular cluster is actually an ensemble of bound atoms that is intermediate in size between a gas phase molecule and a dust grain. And when you apply this to a stellar atmosphere, then you will see that mainly the atoms and isotopes of these atoms are rather close to the star, where it's still hot and dense, and these dust grains are rather found outside the star, where the regions are a bit cooler and we have a bit more distance from the star. So the question here is now, if we want to know more about clusters and these precursors of dust and how the dust nucleates or the dust forms, do we go from this side or do we go from this side? So from the left to the right, from atoms to dust grains, or from dust grains to atoms. So these two approaches can also be called top-down approaches, going from the large macroscopic down to the microscopic, or bottom-up approaches, going from the smallest units up to the dust. And I depicted here on the left side top-down approaches as illustrated by magnesia. Magnesia is magnesium oxide and has one of the simplest crystal structures, which is displayed here. This is rockite or halite and is, as said, very regularly spaced and simple crystal type. And if we take the microscope and look at the smallest unit, we end up here with an 8-atom cube of MgO or Mg4O4, if you wish like that. The bottom-up approach I illustrated at the example of alumina or aluminum oxide. Oxides here are red and aluminum are greenish. And if we start with the smallest clusters here, which is the dimer of alumina, we can make a tetramer. And at some point, so tetramer means 4 units of Al2O3, at some point we will end up at corundum, which is the most stable crystalline form of aluminum oxide. And they can make very beautiful gemstones like here, the ruby or the sapphire. And the question now is, which is better? But before I address this, I will explain you a little bit more what is the top-down approach. So the top-down approach interpolates the small particle properties from bulk analogues. The common theory here is the classical nucleation theory. So just to explain you what this is, a particle or dust grain, for example, the energy is described by a bulk part or a volume part and the surface part. So the bulk or volume part is proportional to the power of 3 of the grain radius or the particle radius and is attractive. That's why it's displayed here at the negative side. The surface energy is repulsive and scales with the surface, which is to the grain radius to the power of 2. The resulting line here of those bulk and surface potential comes then here at the maximum, which is characterized by a critical grain radius and a critical energy, which is called the energy barrier. And that actually this grain radius and barriers characterize the bottleneck in the nucleation approach of a top-down approach of nucleation. And to give you a bit an impression from the daily life, I thought this might be not bad. So top-down approaches essentially work, you take macroscopic bulk, like for example here a bread, and put it in one of these bread cutting machines. And I put this example here because I've never seen such a machine before arrived in Belgium. Found this very interesting to see. And then you cut these breads in slices, and then you have made a 1D cut. But if you slice them 90 degrees or perpendicular to it also, and have a 2D cut, which somewhat remind me on friture. And if you make a third cut, again perpendicular to it, then you end up with cubes. And if we go back to the bread, that reminds me somewhat on the fondue, which me as a Swiss can only recommend it at this season of the year to eat that. So now we're coming to the bottom-up approach. Bottom-up approach calculates the properties of small particles from first principles, or you could also say ab initio, quantum mechanics. And our goal is here to find the most favorable cluster structure. When I say most favorable cluster structure, I mean the cluster with the lowest potential energy, because this will be the most likely to be present in circumstellar envelope. And the mathematical equation describing that is essentially the time-independent Schrödinger equation. And how do I find the most favorable stable cluster? That I find through global optimization technique. There's on one hand classical force fields, which are sometimes also called interatomic potentials, which are not always that accurate, but they're also computationally cheap, means you can calculate them quite fast. Bit more expensive, but also much more accurate are hybrid density functionals, so which relates to the density functional theory. And you can go even on a higher level of theory, which would consist then of post-Hartree-Fock method. But however, these post-Hartree-Fock methods are very limited, in particular for large system size or large clusters, they are prohibitive. So as you already have seen, the cluster size plays an important role and is very relevant, because if the cluster is large, not only the computational effort of the whole system is larger, but also the possibilities of these structures to arrange, or the number of isomers, chemically said, increases literally astronomical with the system size. So if I now compare again bottom up with top down approaches, then we see, okay, the crystal cuts or bulk cuts, they look quite different from these clusters. And here, this is really to scale. This is not half a nanometer, so 4.8 angstroms. And you see here the atomic coordination, the bond length, just the overall appearance is different from these two approaches. And the clusters, they just have quantum and finite size effects. They have different bond characteristics. They don't show periodicity because they're, or often don't show periodicity because they're just too small. And all this leads actually to the point that if you compare them in potential energy, then we see that these bulk cuts have much higher potential energies than the clusters, and do not represent the minimum structures, at least on the nanoscale and sub-nanoscale. So I hope to have convinced you that the clusters or the bottom-up approach is the favorite approach. And actually, I'm also following that approach. Now the question is, okay, that's good. We believe now clusters represent these transitions between the gas phase and the dust phase. But are they observable? And there I say, well, yes and no. Astronomical observations can show, for example, rotational levels, which are depicted here on the left-hand side. So molecules and clusters, they can rotate. And to the rotation, there are corresponding 3 rotational constants, as long as this cluster is not linear. And these rotational constants, they're inversely proportional to the moment of inertia, which means that the larger the cluster grows, the smaller the rotational constants, and vice versa. But we also have vibrational modes, and I try to, excuse me, that was too much, sorry for that. We were here. These vibrations that we can see here for the water molecule, they have also more and more vibration the bigger the cluster size becomes, because the general formula is 3n-6 vibration modes, where n corresponds here to the number of atoms, which means that larger clusters have more and more vibrational modes, and they blur out, and they're getting less and less sharp. Certain attention should be paid, because there are some very symmetric clusters which can rotate, and they can also vibrate, but we can't observe them because they have no permanent dipole moment. There is a certain possibility with certain asymmetric stretching and bending modes to still see them, but it is challenging. So Now, as you have seen, we already entered the quantum world, and to actually go to the quantum chemistry, which is, for me at least, molecular quantum mechanics, I wanted to show two pictures. Here on the left, you see Wolfgang Pauli and Niels Bohr, which they're fascinated about a spinning top, which exerts a spin flip, and they tried to explain that not in the classical sense, but in the quantum mechanical sense. But what even delighted me more is a picture that I found in my family archive, where Werner von Heisenberg and Niels Bohr are depicted together with my grandfather. And I have to say, I'm a bit jealous on my grandfather that he had the chance to talk to these amazing scientists. So talking about quantum chemistry, I want to show you an optimization on the density functional theory level. And here you see actually a cluster of 30 atoms. So this is Al12O18, a hexamer of alumina. And I start optimizing it. You see it goes a bit up, and suddenly here the symmetry breaks and it converges slightly to its minimum structure, which looks like this. Well, and finally, I want to come to the summary of the first chapter of this talk, and want to tell you, yeah, well, dust forms around all stars and is most likely in a bottom-up way via molecular clusters. And dust is also responsible for the stellar wind and the mass loss, and enriches the interstellar medium with solid matter. And I want to thank you for listening, and want to give over to Marie.
Thank you, David. I'll go ahead and start my presentation. Okay, let's go. Present. So David told us all about how dust grains are formed around dying stars. And I would like to talk about the journey that these dust grains go through as they evolve through our galaxy and how they might end up in planets. So as David already mentioned, our galaxy is continuously evolving. Stars are born and die all the time. This is just something we don't really notice on a day-to-day or rather night-to-night basis, because it happens on timescales that are much longer than an average human life. We're talking about millions of years rather than a short century. So David talked about this bit of cycle in a galaxy. So as he mentioned already, stars are formed in the interstellar medium, or the ISM. That's the space in between the stars. It's not completely empty. In fact, there's denser clouds of material, star-forming nebulae, and this is the region where stars are born. Stars like our sun become a red giant towards the end of their lives, then they go through the AGB phase, and this phase is characterized by mass loss. And thanks to the mass loss, the star ejects its outer envelopes back into the interstellar medium, enriching it with a bunch of gas and newly formed dust, what David just told us all about. The only thing that's left over is a white dwarf. Now, massive stars undergo a different type of evolution. So if a star is more than 8 to 10 times massive as the mass of our sun, it will become a red supergiant, and that star will also eject its outer envelopes back into the interstellar medium, but it will not do so in a quiet, controlled manner of an AGB outflow. No, it will explode as a supernova and just throw it all out there. Again, lots of gas, lots of dust. The only thing that's left behind is a neutron star or a black hole. So this galactic evolution cycle we have here, so we have the interstellar medium, stars are born from the interstellar medium, and as they die, they eject their outer layers back into the ISM. And each galactic cycle actually corresponds to chemical enrichment. During the Big Bang, only hydrogen, helium, and a little bit of lithium was formed. Everything else has been forged in the hot cores of stars through nucleosynthesis. So all the carbon in our bodies, the oxygen in the air, the heavy metals in our computers, they've all been formed in the cores of stars that have died a long time ago. So with each cycle, stars are born, and as they eject their outer layers, they also enrich the ISM with chemical elements formed in their cores. So chemical enrichment happens. And as we go through the cycle, we can identify many astrochemical laboratories. AGB outflows are only one of them. And by studying the molecules present there, we can we can try to understand astrophysics a bit better. So astrochemistry as a tool to understand astrophysics. So far, about 200 different types of molecules have been detected in the interstellar medium or around evolved stars. So this slide shows all or most of them. And most molecules are rather simple, composed of only 2 or 3 atoms. The most abundant molecule is H2, because well, H is the most abundant atom. Then CO is the second most abundant molecule because, well, there's still a lot of carbon and oxygen. And as David just said, carbon monoxide has a very strong bond. Then we also have some table salt floating around, some water, and some toxic hydrogen cyanide. On the other end of the table, we have well, the larger molecules. So benzene contains 12 atoms. That's a lot for space. And we also have these buckyballs that are formed likely in the outflows of evolved stars. So 60 and 70 carbon atoms just in a ball. If you look at the middle bit, it's clear that there is an organic footprint to this. So there are a lot of carbon chains going on, and some of them we know from here on Earth. We have formic acid, methanol, methylamine, and also the smelly ethyl mercaptan. But there's also more exotic species that you wouldn't really encounter in your room or even in a laboratory. Maybe silane isn't so exotic, but it certainly causes less explosions in the interstellar medium. But then there's these carbon chains, well, quite literally carbon chains, just 5 carbon atoms in a row. That's a molecule that exists. You can add a nitrogen at the end or a hydrogen at the other end as well. But these are very exotic species. And the existence of these molecules, and more specifically these weird guys, tells us a lot about the environment in which they are formed, because astrochemistry is very different from terrestrial chemistry. Chemistry takes place in an environment that is very different from a lab. So it's not at 1 atmosphere of pressure or at room temperature. We're talking about very high or just low densities, high and low temperatures, difficult to create in a lab. So studying the presence of these molecules in astrochemical laboratories tells us a lot about the densities and the temperatures, so helps guide the astrophysics. But on the other hand, astrochemistry is also useful for regular chemistry, since it opens up this whole exotic array of chemistry and it allows us to probe these extreme ends of, well, our parameter space. David already mentioned that we detect these molecules thanks to their rotational and vibrational transitions. And these transitions, well, they emit a photon in the submillimeter to radio wavelength regime of the electromagnetic spectrum. To detect them, we need enormous satellite dishes, much like satellite TV, but then a bit more sophisticated. This is the IRAM 30-meter telescope. It's located on the Sierra Nevada in Spain. And then here on the right, we have the APEX telescope on the Atacama Desert in Chile. So both these telescopes are in a desert on a mountain. For astronomical observations, you really want to put your telescope on a mountain because then there's less atmosphere between you and your object. The atmosphere is very nice for us to live, but if you want to do astronomical observations, it's very annoying. So you put your telescope on a mountain to decrease the amount of atmosphere. You also want it to be a dry place, so a desert is perfect since, well, water absorbs a lot of the radiation that we are interested in, a lot of the bands where the molecules, interstellar molecules, their fingerprints are absorbed by water. So we should avoid water and an atmosphere. Now, the best way to do this is to send a telescope to space, but that's a bit expensive. There used to be a space observatory, Herschel, that operated in the sub-millimeter, but well, it was only operational between 2009 and 2013. James Webb Space Telescope will be launched soon, hopefully, but so far it hasn't been launched yet. So we have to do with the next best thing, which is ALMA. It's also located at the Atacama Desert, and actually it's a bunch of apex telescopes working together. It's a radio interferometer, and that's very simplistically a group of telescopes working together and pretending to be a much larger telescope. So we can pretend to have a dish of a kilometer wide, for example. It's not possible to make something. And ALMA is a real astrochemical workhorse. It has done a lot for the astrochemical community because it has increased our spatial and spectral sensitivity. And just to show this, here is a spectrum of IRC 10216. That is an AGB star that David just talked about. On the red, in the red, it's a spectrum taken by the IRAM telescope. And then the black line is a spectrum taken by ALMA. So same star, different telescope. In fact, the bottom one here is zoomed in. So in IRAM, we can already detect several molecules, but if we use ALMA, the sensitivity increases and there's so many more lines that we can detect. And see a lot of U's floating around on the screen. That's not uranium. These are unknown lines. Then this again highlights an interaction between astrochemistry and regular chemistry, because we need spectroscopists to measure the spectrum of the molecules so we can try and identify them in space. So let's now take a look at astrochemical laboratories along the way. Our dust grain has been produced around an AGB star, and it has entered the interstellar medium, where stars are formed in dense clouds. This is an image in the visible of a dense cloud. And they are also called dark clouds, and I think it's quite clear why they are, because it looks like there's a hole in the sky. There isn't a hole in the sky, fortunately. It's just a bunch of dust and gas that is blocking our line of sight. If we switch to a different, longer wavelength, so if you go to the infrared, we can see through the dust and gas, and in fact, everything's still okay. There's a bunch of stars behind the cloud. In fact, this cloud is on the verge of collapse. It just needs a tiny push, perhaps a supernova going off in the distance, for it to go out of equilibrium and collapse onto itself, forming stars. But so far, so good. It's still in a very precarious equilibrium. And I'd like to highlight the importance of dust, because it's because of the dust that we cannot see through this cloud. The dust shields whatever's going on inside of the cloud against visible light, but also against more energetic ultraviolet light. And that's a very important quality, especially in the interstellar medium. And because, well, life isn't easy in the interstellar medium, especially if you are a bunch of atoms that want to become a molecule. So most of the material in the ISM is located in diffuse clouds. And a diffuse cloud is not completely empty, but it's getting close to it. There's only 10 to 100 particles per cubic centimeter. Now, in this room, there's about 10 to the 20 particles per cubic centimeter. So it's not a void, but it's very empty. These low densities will make forming a molecule quite difficult, because you need a collision between atoms before you can form a molecule. And at such low densities, it can take quite some time before two atoms collide. It can take years, even up to a century, before a molecule can form. But that's not really an issue, since we are pretending to be gas in a diffuse cloud, and the gas is going to spend a couple of hundreds of thousands, maybe even 1 million years in this diffuse cloud. So even if it takes a century, we have time, everything's fine. What is the real issue is that you're still in the interstellar medium. So the space in between the stars, you are surrounded by stars and they radiate part of their energy in the ultraviolet. So there's a bunch of UV photons floating around, and the likelihood of one hitting you is quite high, since you're not shielded by anything. You're in space, there's no atmosphere, there's no dust shielding you or whatever, you're in a diffuse cloud. And as soon as a UV photon hits a molecule, it can photodissociate the molecule and they'll break it back up into atoms. So low density and high UV radiation make for a very simple chemical composition. It's mainly some atoms, simple molecules such as H2 and CO, of course, but for example, also CH, and they're positive ions because a UV photon also likes to knock out an electron. If we go to a dark cloud, the density increases to 10,000 to 1 million particles per cubic centimeter. So that's dense for the interstellar medium. But if we go to the analogy here on Earth, that's about the density that can be created using ultra-high vacuum pumps. So what is ultra-high vacuum here on Earth is actually quite dense in the interstellar medium. Astrochemistry is very extreme. But thanks to these larger densities, the likelihood of atoms colliding becomes larger, and you have all this dust shielding you against these UV photons that are out to photodissociate you. This means that more complex molecules can be formed. And in astrochemistry, we're not so picky. H2O, H2CO, HCN, the weird guy C4H, that's already quite complex to us. But there's also genuinely complex molecules that are formed. These complex organic molecules, ethyl formate, methanol, and formic acid, for example, others as well. And their detection was quite surprising, since gas phase chemistry alone cannot explain the abundances with which these complex organic molecules were detected. Because, well, to form ethyl formate, you still need a lot of collisions to happen before you can make such a long molecule. And again, the dust particles come to our rescue, because the dust provides a catalytic surface for the chemistry to happen on. These dark clouds are quite cold, so gas phase species are able to accrete onto the dust. So here we have a bunch of CO molecules, and these hydrogen atoms are zooming around. They're much lighter, so they can hop over the dust quite efficiently. And here methanol was formed on the dust grain. So a CO molecule arrived from the gas phase. Hydrogen is still zooming around and hydrogenating those CO molecules. Even though they are heavier, they can still, well, scan the surface, and a more complex molecule is formed. Again, CO arrives from the gas phase. These two HCOs meet each other on the grain surface. So again, the surface acting as a catalytic surface for chemistry to happen on, and poop, glycolaldehyde is formed. And well, this continues and continues. Another CO is added from the gas phase. And now a UV photon hits methanol, breaks the hydrogen bond, and then these two radicals can combine and form glycolaldehyde. Now, this is still quite a slow process, but again, we have time, we have plenty of time. And over time, the grain surface becomes covered in an icy mantle of complex organic molecules. And as our dust grain becomes incorporated in a star-forming region, it's heated up, and thus it evaporates its icy mantle, releasing these complex molecules into the gas phase where we can observe them. So dust plays a twofold role. Firstly, it shields against UV radiation, photodissociates, and secondly, it provides a catalytic surface for complex molecules to be formed on. So our cloud has collapsed, stars are being formed, and this is an artist's impression of a later stage in star formation. So here at the center, we have the protostar. So a dark cloud collapses, everything goes to 1 point more or less. At the core, we have the protostar. And the protostar is surrounded by a disk of material, which is currently in this picture, still accreting onto the protostar. And this disk of material is also called a protoplanetary disk, since this is a place where planets are formed. And well, yeah, planets are a regular byproduct of star formation. That's something we know. But not only are planets formed in this region, there's also meteorites that are formed and comets. And if you want to do some archaeology and try to determine the composition of the protoplanetary disk from which we and the Earth is born, we can try to determine the composition of comets to figure out what our initial protoplanetary disk composition was. And in 2014, the Rosetta mission of the European Space Agency reached the comet 67 Churyumov-Gerasimenko, or 67P. And it has done a lot for astrochemistry as well. So this is a picture of the nucleus of the comets. So comets were commonly described as dirty snowballs, but that's not really a dirty snowball. It's more a bath duck, if it has to be something. And you see these rays radiating away from the nucleus, and that's actually gas evaporating from the surface. So the comet is covered in icy material. As the comet comes closer to the sun, it's heated up, and the icy mantle evaporates from the surface. So that's what we see here. I particularly this of also taken Rosetta. So this is the surface of the nucleus of the comet. There's a bunch of rocks lying around. There's also a cliff that's some 13 meters high. And there is a bunch of stripes that you see. That's actually, but that's not real. It's cosmic rays hitting the detector, but you also have these specks of dust floating around, and that's actual snow on the comet. So here we have the geology and the weather on the surface of a comet orbiting our sun, which is pretty cool. Now, Rosetta has detected many organic molecules, and the most exciting one has been glycine, the simplest amino acid. So the simplest protein essential for life is formed on a comet. Well, has been detected on a comet, formed purely via astrochemical processes. And this opens up the question towards our own origin and what fraction of life is or can be inherited from astrochemical processes. And these days, we are no longer limited to a sample size of just one, so our solar system in its current evolutionary state. We can study many other planetary systems and also the birth of planetary systems by studying protoplanetary disks. And this is an actual observation, not an artist's impression, of the protoplanetary disk surrounding HL Tau. And the next speaker, Robin, will tell us all about planet formation.
All right, thank you very much. Now we do the shift.
Yes. Oh.
All right, good evening, everyone, and thanks for joining this three-part lecture. So we are now arriving at chapter 3, where I will explain how the dust coming from the dying star and the outflow of dying stars has gone through the interstellar medium and has arrived at the protoplanetary disk. How this dust will now act in how to form planets, and also how this will change a little bit the atmospheric chemistry of those planets. So first of all, for continuity, of course, I show again the picture of HL Tauri, the protoplanetary disk that Marie has also shown, where you indeed see in the center this forming star. So it's a super young star, still gaining mass and still gaining luminosity. And then around it, this nice disk with these gaps. And in these gaps is really the place where we expect planets to form. Now, this is an image taken in the radio wavelength. We can also look at this in the visible light, and then it looks a little bit different. Then you see here a collection of these protoplanetary disks, and you really see this. These are huge structures of many, of a lot of gas and dust. And then right in the center, there is where we would expect the planets to form. So I will tell you a little bit about the theory of planet formation so that we're all on the same basis. So as I already said, the planet formation will take place in the middle section of the disk. And why is that? Well, there the densities are the highest, and there you also are shielded from the intense radiation from the star, as in the process that Marie already explained. And there you have this nucleation for these dust species. So it's like micrometer sized dust species. And if you have not cleaned in a while your house and you look in the corner of your house, you can see that dust likes to stick together via electromagnetic forces. So they really want to form planets, actually. So they do it automatically in your house. But here, this is done, of course, on a bit larger scale. And these dust species start to stick together until they form something like millimeter-sized pebbles, like small rocks. And all these rocks are rotating around the star in such a disk. Then these rocks, they also collide and they stick together, and they slowly build up until you get bigger rocks of meter-sized and then even larger. And then at some point, a few of these rocks become so large that they will really accrete everything in their neighborhood. If they pass a certain mass threshold, they even have enough gravity to accrete the gas from the disk. And this is the way you can form giant planets, because the gas giants in our solar system, they are consistent mostly of gas, of course. And then finally, there's a kind of dynamical phase where the first planets that have been formed are dominating the dynamics and accreting other smaller bodies and kicking other bodies out of the planetary system, until you end up with something like our own solar system, or maybe something different. We don't really know yet. And this theory of planet formation, it's a good theory. It has a few difficult parts as well, mostly because there needs to be a huge growth on a very short time scale. So this growth is really 15 orders of magnitude that needs to be covered, because you have to go from like this small micrometer sized dust grain to a planet of 10,000 kilometers. And this has to happen on a very short time scale, because, as I said, to form giant planets, it's really a race against time. They have to accrete enough gas from the disk, but we know from observations that the gas dissipates after a while. And after around 10 million years, all the gas in the disk will have dissipated, and you cannot accrete it on the planet anymore. So if the planet is not formed before this time, you will never get your giant planets anymore. So 10 million years sounds maybe like a lot of time, but in astronomical timescales, it's really, really short. And then finally, these collisions that need to happen for the growth of the planets, they need to happen slowly, of course, because you can imagine that if you have two bodies of something like 10 or 100 meters, and they smash into each other at high velocities, well, you shatter everything, everything breaks up, and you have to start all over again with your planet formation. So that's not helpful, of course. So we really have these observations from the small dust grains on the one hand, of which I already showed a few pictures. And we have, of course, observations of planets in our own solar system, but also exoplanets, planets around other stars. So we now know of more than 4,000 of those already. But in between, it's a little bit more difficult. We don't have so much information. But I will talk about two types of observations that may help us in order to constrain these conditions of planet formation. So the first one will be the transition disks, and the second one I call chemical fingerprints. So first, the transition disks. What is a transition disk? Well, very simply said, it's like a star with a disk around, and the disk is already quite evolved and is slowly opening a gap inside. So it's kind of an evolved protoplanetary disk already. And there's one specific case that I would really like to talk about, and that is the case of PDS 70. This is a sun-like star that is being formed, and it has a disk with a gap inside. So it's a transition disk. And there has been a very interesting observation by the ALMA telescope. So it's pictured here. So this is like this huge array of radio telescopes who looked at emission of this ion HCO. And the emission of that ion looks like this picture. So in the center, you see the star. And then the bright emission part or ring around it is the disk. And then you see here between the disk and the star, you have some sort of gap opening where we would expect planets if they are being formed there. And because this is a talk for chemists, of course, I specifically looked up the chemical reaction for this ion. And the main reaction pathway is that it is formed from CO, carbon monoxide, as was already mentioned a couple times, a very important molecule because it's such a strong bond. So that means that you can find it quite close to the star. And also hydrogen or a hydrogen ion, which is of course plenty available in the universe. And then this will make this HCO ion that you can, and that's a really good way to probe very close regions that are very close to the star, because that's where you can expect it. All right, and why is this now such an important object, or why do I want to talk about this? Well, a little bit later, there was another observation, not in the radio wavelength, but in infrared. And they saw that here actually is a planet forming inside this gap. So this is the picture in the infrared. Here in the center, there's again the star, which has now been covered because it's too bright otherwise. And then this is the ring around it. The dark region is the gap. And here you see very clearly this bright spot. That's the planet that is being formed. So it's really a baby planet. It's just born. And the orbital distance of that planet is around 22 astronomical units. So that is comparable to the orbital distance of Uranus. And the age of the system has been determined to be around 5 million years. So this is really good evidence that our current way of thinking about planet formation, that it still works out. You really can form these very massive planets. So the mass is 5 times the Jupiter mass, or up to even 40 times the Jupiter mass. You can really form these massive planets in a very short time. So this is really good evidence that we are on the right track. And actually, another very interesting discovery has been made 1 year later, 2019, and there it was found that there is actually a second planet in this system. So this is, again, a picture in another wavelength range. This time they were looking at the emission of the H-alpha line, which is a good tracer for accretion. And you see where here is the star, and here you have these two very bright regions where you find this H-alpha line peaking. So there's really a place where a lot of gas is accreted onto an object. So you have here the position of the planet that was already known, and here you see the second planet. The second planet is a little bit lighter, and it orbits around 35 AU. And quite interesting is that the orbits are in resonance. So for every couple of orbits the one makes, the other one makes another couple of orbits, but they are resonant. And that is quite interesting because it could be kind of analog to Jupiter and Saturn, who also have resonant orbits. So these kinds of observations are super interesting because they really allow us to see planet formation right when it is happening. And this is the first thing that I wanted to mention that can constrain planetary evolution, planet formation theory. And the second one were the chemical fingerprints. And for that, I would really like to show the mass metallicity relationship that happens, or that is visible in the solar system. And it's a relationship between the mass of the solar system gas giants and the metallicity of these planets. Now, the metallicity, what does this mean? Then I have to show you the periodic table of elements for astronomers, and that looks like this. So you have here, of course, hydrogen, you have helium, and all the other stuff we just call metals. Because there are so few of them, we just call them metals. It's very easy. And the metallicity, that means the amount of metals compared to hydrogen. So if you have a high metallicity, you have many metals compared to hydrogen. So this relationship between the mass and the metallicity, we can plot it for the solar system objects. And then you can see that all the gas giants in our solar system, they fall nicely on a certain line. So here on the x-axis is the mass, on the y-axis is the metallicity. And you see that the more massive the planet is, the lower the metallicity is going to be. And this is actually a good indicator of this accretion scenario that I already talked about, because you can imagine a planet being formed from these solids, these giant rocks, and at one point they become massive enough to have certain gravitation, and then they start accreting gas from the disk. And this gas accretion, of course, it increases the mass, which increases the gravity, which increases the accretion. So it goes quite quickly. And you see that if you accrete more and more mass, well, then you are, if you accrete more and more gas, then of course the metallicity will go down because the gas is not a metal. So this is really a good indicator of this core accretion. And it would be, of course, very interesting to see if this is the case for all planets also outside of our solar system. So we will come back to that later. Another interesting thing to probe in the protoplanetary disk is really not just the bulk metallicity, but really the chemical elements. So one important one there is the carbon to oxygen ratio, which is plotted here. So the carbon to oxygen ratio is plotted as a function of the distance from the star. And you see here different lines. The solar line is the reference line. And then the solid line here is the gas phase, the carbon to oxygen ratio in the gas phase. And then the dashed line is the carbon to oxygen ratio of the solids. Now, you see that if you start at the sun, so it's to the left, and you go farther and farther away from the sun, or from another star, for example, at some point around 2 astronomical units, the temperature drops enough so that water can start to freeze. So then we call this actually the snow line, so you can form snow. And if water freezes, it will, of course, condense out of the gas phase, and it takes with it a bit of oxygen. So the carbon to oxygen ratio in the gas phase goes up. Then you can continue outwards, and then you have carbon dioxide here that starts to condensate. And well, it has a carbon, but 2 oxygens. So it still takes out more oxygen than carbon. So the carbon to oxygen ratio again goes up. And then finally, it becomes so cold that even carbon monoxide will freeze. And then, well, then there's no carbon or oxygen in the gas phase anymore. So why is this important? Well, actually, this shows that there's a gradient of the carbon to oxygen ratio in the protoplanetary disk. So if we have some way to find out what the carbon to oxygen ratio in a planet or an exoplanet is, then we can more or less find back where in the disk it was formed, because it's from that location that it has accreted its material. So this is something that we really want to try to do. Or if you put it in summary, the elements that are accreted during the formation, they may be detectable in the planetary atmosphere. So for our solar system planets, this is, of course, quite easily, well, I say easily, but it's not so easy, of course. but it's relatively easy to detect. You just send a space probe to there to measure the water content or the methane content in the atmosphere, for example, and then you have your answer. But for exoplanets, it's not so easy. However, sometimes it is possible to detect the chemical composition of their atmospheres. So this happens when sometimes an exoplanet orbits around its star, and sometimes it comes in front of the star. So depending on where you are looking at the star, it comes between you and the star. And when it goes in front of the star, the light that we receive from that star is filtered through this atmospheric layer of the exoplanet. And then from analyzing that light, we can actually see which kind of elements are present in the atmospheres of exoplanets. So this is something that we can't do for a long time yet, but we are getting better at it. And one of the main results from this kind of exoplanet atmosphere analysis is that we find a lot of water. So this water in the gas phase, and also I'm mainly talking about giant planets, so not rocky planets with liquid water. That's something completely different. So it's really giant planets with water in the gas phase atmosphere. And there's like some 30 to 40, I think, planets who have this kind of water detection for them. And then some others that are quite regularly detected are sodium and potassium, because they have very strong adsorption lines. And that's why they are easier to detect. But then it becomes quite difficult after that. So there are a couple of other molecules that have been detected, maybe, maybe not, or in some exoplanets, and definitely not all of them. And I list a couple of them here. So there are some quite exotic ones like titanium oxide, vanadium oxide, but also some more expected ones like carbon monoxide and carbon dioxide. Here you have hydrogen cyanide, and here you have methane. But really not so many detections of them, and if they are detected, usually with huge uncertainty error bars on them. But actually this methane one is quite interesting, because if you have a detection of both water and of methane, water has oxygen, methane has carbon, and then you can really have a good guess on what the carbon to oxygen ratio in that planet would be, and then we can connect it to planet formation theory. Now, in order to interpret all these observations, we also need models, of course, so chemical models of the exoplanet atmosphere. That's another part that will be needed. And this is more my field of expertise. And what you can use for that is a chemical network. So some people also call it chemical mechanism, I've heard, and I don't know how chemists call it, but what I mean by it is that it is a collection of reactions with a collection of rate coefficients. That all gives you nice differential equations that you can solve with respect to pressure and temperature and time. And if they are solved, then you know actually the chemical composition of the atmosphere. So in principle, it's quite simple. However, there is a big difficulty, and that is that you need all the reactions and all the rate coefficients, of course, because sometimes not all the reaction mechanisms are known, or sometimes the rate coefficients are not so accurately determined, and then you can, of course, get errors. So these are not always available. A solution might be to use a chemical network that is experimentally tested, but then, yeah, you have to figure out a way to build an exoplanet in a laboratory. That might be a bit difficult, you would think, but actually it's quite all right, because we can use here industry, and we go from a car engine to a hot atmosphere. So maybe a bit unexpected, but really car engines help us a lot to understand exoplanet atmospheres, because the car engine operates in a temperature regime of 100 Kelvin to 1000 Kelvin roughly, and the exoplanet atmosphere also operates in that regime. And then you have a car engine which has to operate from 0.01 bar to 100 bar, and exoplanet atmosphere also operates in that regime. Then in the car engine, you are mainly dealing with combustion reactions, so carbon, nitrogen, oxygen, hydrogen. These are also the atoms that we would expect in an exoplanet atmosphere. But the difference between the two is that there is extensive experimental data and studies done on combustion reactions for car engines and not for exoplanet atmospheres, of course. So we can use information from industry to apply to our hot atmosphere. So that's very nice, of course, that we can make this connection. All right, and what do we get then when we combine all these things? So we have the observations on one side, spectroscopy, and also the modeling of the chemical atmosphere. And then we can really start to go back to where we came from and to find out these clues for planet formation. And I show again the mass metallicity relationship. So the single line with the 4 solar system bodies on it, but now populated with exoplanets as well. And well, here is still the line with the solar system bodies. You have here Uranus, Neptune, Saturn, and Jupiter. And then these are all exoplanets that have their abundances determined. And you see, well, it's a little bit of a mess. The error bars are still quite big, but it's starting to get to a point where we have enough exoplanets to do these kind of studies on. And the error bars are also slowly decreasing and getting better, especially in the next generation when we will have the James Webb Space Telescope that Marie also mentioned. So this will really give better data, and then we can really try to start seeing differences in planet formation for different systems. All right, and then that brings me to the conclusion of my talk and also to the conclusion of the whole lecture. And that is that we talked about chemistry in space. We talked about quite extreme conditions. We had outflows in dying stars. We had the cold vacuum of empty space with irradiation, UV radiation. And we had the hot irradiated exoplanets. And actually in all these very extreme conditions, very hostile conditions, chemistry happened. Chemistry is happening universally, and we can use our chemistry that we know from Earth to really interpret results in space. And that is in some way really amazing. So really quantum chemistry computations, laboratory measurements, kinetic rate determinations, even industrial testing from car engines, they are all helping us to answer the fundamental questions of where does life originate? How do planetary systems form? Is the solar system unique? Are there many like that? And are we alone in the universe? And with that, I would like to end. And I guess that there is still some space for questions.
Okay, David, Marie, and Robin, thank you very much for this nice story. I think it was a whole new field for most chemists, I think, but you really explained everything from the understandable basics. And I will now go through some questions. So everyone, Robin and David, you can unmute yourself, because I guess I will ask the questions to someone, but everyone can answer, of course. So my first question is one for David. So you clearly have a preference for the bottom-up approach.
Indeed.
Is this more a personal preference, or is the top-down approach a bit old-fashioned or used for other approaches? Can you comment on that?
Yeah, well, so the top-down approach essentially arises from, I think at least from meteorite people that gathering a meteoritic stone. And I mean, they must kind of grind it into smaller units and actually to make the analysis what is actually inside. Of course, you can use some microscopes, but these dust grains are in a matrix in this meteorite. So we really have to crush it.
Yeah.
And as I tried actually to say, really the global minimum structures are very apart from crystalline analogs, at least, and these small scales below 50 nanometers, I would say. And I think since the bottom up approach also mimics more the dust formation process, because you really describe what is happening in stars, around stars, that they grow in size. And I would say top-down approach is kind of a reverse engineering. And I don't say that top-down approaches are wrong, but that just goes until, I would say, let's say 50 nanometers down, it works, and then you start getting difficulties.
Okay, thank you. The next question is more, was in the topic of Marie more. So I'm wondering the molecules and then the more exotic molecules you mentioned, when they are formed and they are detected, of course, do they live long at that place, or are they just detected and are they maybe just very short living?
They can actually live for quite some time up until they react with another species, but it's mainly because of the lower density. So if you would put a molecule like C5 in this room, it would be hydrogenated in no time, but because of the low densities, they do live for quite some time. But then, yeah, well, these astrochemical laboratories evolve. So over time, you might see a shift in the composition, but we can still detect them, and it's not for a short fraction. Depends on the environment, of course, but they can live for quite some time, much longer than here on Earth in any case.
Okay, then in the chat, there also, the Q&A questions, there are also quite some questions. So I think, yeah, that's maybe an extension of my previous question. Is it possible to capture certain molecules and atoms out of space? I'm mainly thinking in long space travel where it can be useful to capture H2 out of space.
I can maybe answer
Yes,
that since it's in the same line. Well, you could go ahead and try it, of course, but to capture molecules, well, you first have to go to space and the density is quite low, and I'm not quite sure if surely it's possible, but it's maybe not as useful since you first have to get there and then you have to get it back. What is something that is currently ongoing is the OSIRIS-REx mission of NASA, who sent a mission to an asteroid. I think it's asteroid Bennu, if I remember correctly, where they had an arm and it grabbed some bits of the asteroid, stored it inside, and it will return like in a year or so back to Earth, and then we can study the meteorite dust or asteroid dust, a bit like going to the moon and collecting some stones. So for rocks you can do it, but for gas I think it's possible, but very expensive for nothing quite useful, I think.
Okay, the next question is more in line for Robin's topic. Robin, is there a relation between gas dissipation and the number of stars, binary versus single?
Okay. Well, I don't know. But it is true that many stars are formed in binaries. So it's like just instead of one single star, you get two stars, and sometimes with a disk around both of them if they are very close. But I guess they can also be gravitationally bound and have their own planetary system around them. So all of these scenarios can happen. And even it might be that, so for the gas dissipation, I don't know, but it might also be that our theory of planet formation is maybe not correct, and that planets actually form as an extension of stars, so not via slow accretion from the bottom up, as to use some terminology that David already used, but that really planets also form from this gravitational collapse of clouds. So that's also another theory. Now there's a little bit less evidence for that, so we still think core accretion is the best one. But in that case, yeah, then you actually are already forming planets like they are binary stars. So yeah, it's a bit complicated indeed.
Then for Robin also, a more conceptual question, I think, about one of your last slides. So someone asks about the engine exoplanet analogy. So I would assume photochemistry must be really important in an exoplanet orbiting a star. Does your analogy with the engine, so where there is no photochemistry, imply that photochemistry is not that important?
No, that doesn't imply it, because photochemistry can indeed be quite important. In the modeling that we do for exoplanet atmospheres, we take, for example, as I explained, the chemical network from the car engine, but we also use photochemical cross sections, and they are usually from laboratory data. So we combine those two approaches to get really also the photochemistry into the models. And that can be indeed quite important. We're still not really sure how important, because most observations that we have now from exoplanets are mostly from the hot ones, from the gas giants, the hot Jupiters, as we call it. And then photochemistry might be a little bit less important than in cold planets, where photochemistry can really penetrate quite deep into the atmosphere and change the chemistry in a more profound way. But that's still something that is discussed, actually. Yes, that's researched actually.
Yeah. Yeah, a lot of questions popping up at the moment. How can scientists make use of various telescopes? Do they have to request time to use the telescopes by presenting their research, or are the telescopes constantly measuring and making their observations public for everyone? And how long do they have to wait before they have gained data from the telescope? I see everyone giving a reaction, so I think everyone can comment on this.
Yes, so I mean, you need to make a proposal to get observation time. This is true, absolutely. And yeah, depending on how good your proposal is, you need to repropose it. So there's not always a very good acceptance rate, and you really have to have a decent proposal to do that. The telescopes are constantly measuring, and you also need to gauge them, because they're, I mean, Earth-based telescope, they're depending on the weather. Even if they're built on the top of the mountain, you can have day-night changes and so on. You need to calibrate them, actually. And the observation public for everyone. So for certain telescopes, ALMA policies, that is the observation must be open access, so at least the raw data, so far I know.
Yeah, so in fact, for example, for ALMA, I think the last cycle there was an oversubscription rate of 6, which meant that the astronomical community asked for 6 times the amount of time that ALMA can actually function. So then decisions need to be made if there's only that many hours in a day or in a night for a telescope to work. So.
Okay. Yeah, there are a lot of questions, so maybe I suggest that if they have still other questions, they just contact you personally. Maybe one last question, philosophy question, maybe, referring, a nice one to end, referring to the last slide, are we alone in the universe? What do you think?
Maybe I can try.
Go ahead, please.
Because, well, of course, the answer is we don't know yet, but it would be very weird if we are the only ones in the universe, because there are so many stars. There's also so many galaxies even. The distances are huge. So it depends maybe on how you define alone. If you are, we probably are not the only form of life in the universe, but it might be that we are so far separated that, yeah, that we are in that sense alone, just because of the huge distances. But I think, yeah, many people are still, I think, in our community, well, thinking that we aren't alone, that extraterrestrial life must exist, and that we are looking for it in our own solar system, but now also in exoplanets. So yeah.
And then one last question, because we work in the Q&A section with a kind of voting up system. And there's one that has some votes. So have more complex amino acids than glycine, as a few already mentioned in the talk, been observed in space? If not, do you expect they will be?
So I think glycine is the most complex molecule, but it's definitely the only biomolecule that has been observed so far. Maybe others are able to form as well, but so far there's no evidence of their existence. So the data of the Rosetta mission is still being analyzed. Maybe something pops up, maybe not, but well, we can get to glycine just through chemical processes on a dust grain. So we don't know yet. So far, it's glycine, the most complex and also the only biomolecule.
Okay. If no one of the speakers wants to add something to that, then yeah, David?
No.
Okay, then I think we can end here our talk. I really want to thank you, well, the three of you, for your very interesting talk and the interactive discussion at the end. Normally, yeah, we would have a present for you, but it's difficult to give that in real life, of course, but that will follow for sure. So yeah, thank you very much. And also thank the participants for joining us this evening. And yeah, have a good evening and see you the next month. Bye.
Right. Thanks.
Thank you very much for listening. Bye.
Bye.